Tonight, my friend, you'll fall asleep to the story of Nikola Tesla, the mind that helped electrify the modern world, dreamed beyond his time, and turned invisible forces into the machinery of the future. So get comfortable, and let's drift into the quiet history of electricity together. Chapter 1. The Mind of Nikola Tesla. To understand Nikola Tesla, it is not enough to say that he was an inventor, or even a brilliant one. Many inventors improve existing devices. Many engineers solve difficult practical problems. Tesla did those things, but the more unusual part of his story lies in the way he seemed to think about the physical world itself. He approached electricity not merely as a useful force to be tamed for industry, but as a deep pattern in nature that could be understood, shaped and extended into entirely new systems. He became one of the central figures in the rise of modern electrical technology because he did not look at isolated machines first. He looked for invisible principles. In that sense, the mind of Tesla was not defined only by cleverness, but by a rare ability to move from abstract physical intuition to concrete engineering design. Tesla was born in Smiljan in the Austrian Empire, in what is now Croatia, to Serbian parents, and he grew up in a world far removed from the electrified cities with which his name would later become associated. His father was an Orthodox priest, and his mother, though not formally educated in the modern academic sense, was remembered for her practical skill in making tools and household devices. Tesla later credited her with shaping part of his inventive impulse. That detail matters because it reminds us that technical imagination is not born only in universities or laboratories. It can begin in the close observation of how useful objects are made, repaired, and improved. Accounts of Tesla's early life often emphasize his extraordinary memory and his capacity for mental visualization. It would be easy to turn those descriptions into myth, but there is a more grounded way to understand them. Some people develop unusually strong spatial reasoning, allowing them to rotate objects mentally. Imagine moving parts and test arrangements in the mind before touching physical materials. In modern cognitive terms, that kind of ability can be linked to strong visual imagination, working memory, and pattern manipulation. Tesla appears to have possessed such capacities to a remarkable degree. He described designing machines mentally and then returning to those imagined devices later to inspect them, almost as though they had been physically running in the meantime. Whether every retelling of this habit is exact in every detail is less important than the broader pattern. Tesla consistently worked as someone for whom ideas took on vivid physical form before they entered matter. That habit helps explain why Tesla later stood out even among gifted engineers. The late 19th century was full of talented people working on electricity, magnetism, telegraphy, and power generation. But many of them advanced by incremental trial, repeated testing, and careful improvement of known methods. Tesla certainly experimented, but his deeper strength was often conceptual. He tried to see the system behind the apparatus. This difference would become crucial when he confronted one of the great engineering questions of the age: how to generate and distribute electrical power efficiently over long distances. The answer that transformed the modern world did not come from thinking only about a lamp, a wire, or a generator as separate objects. It required seeing the behavior of fields, currents, phases, and motion as parts of one coherent whole. Part of Tesla's scientific importance comes from the fact that he worked in a period when electricity was shifting from curiosity to infrastructure. Earlier investigators had studied electrical and magnetic effects with growing success, and figures such as Faraday and Maxwell had already revealed profound laws of electromagnetism. By Tesla's time, the question was no longer only what electricity is, but how it could be made practical at scale. How could it light streets, drive machinery, power factories, and reshape daily life? This was one of the great transformation points in modern civilization. Tesla entered that moment with a mind unusually suited to it, because he could move between theory-like intuition and hardware-like concreteness. He was not primarily a mathematical theorist in the style of Maxwell. He was a systems thinker with experimental daring and strong physical imagination. That distinction matters because Tesla is sometimes described too loosely as a physicist in the pure academic sense. His legacy belongs more precisely to electrical engineering, applied electromagnetism, and technological design, though his work constantly touched physical principles. He did not reshape physics in the way Einstein did, by overturning the conceptual foundations of space and time. Instead, Tesla helped reveal what established electromagnetic principles could become when translated into robust technological systems. His genius was not chiefly in writing the deepest equations of nature, but in recognizing which hidden physical relationships could be turned into working devices of enormous consequence. This is why his most important achievements were not just inventions in isolation. They were linked ideas, patents, machines, and demonstrations that helped create the practical world of alternating current power. The best way to describe Tesla's mind, then, is as a mind of dynamic relationships. He did not merely think of electricity as something flowing down a wire like water in a pipe. He thought in terms of oscillation, periodic change, magnetic interaction, resonance, and motion emerging from invisible structure. These are not trivial differences in style. They reflect a deeper sensitivity to the behavior of electromagnetic systems. When Tesla later discovered and patented the rotating magnetic field, he was not simply finding a useful trick. He was recognizing that alternating currents, arranged with the right phase relationships, could create a magnetic pattern that turned in space and could drive mechanical motion without the limitations of earlier designs. That insight was both elegant and practical. There is also a psychological side to Tesla's mind that cannot be ignored. People around him often described him as intense, disciplined, and at times extreme. He cultivated regular habits, had powerful preferences and aversions, and could pursue ideas with near-total concentration. Some later descriptions of his behavior suggest traits that today might invite discussion in terms of compulsive tendencies or atypical sensory experience, though it would be careless to impose modern diagnoses too confidently on a figure from another era. What can be said more safely is that Tesla combined brilliance with rigidity. The same mind that could sustain extraordinary focus could also become consumed by singular visions. His early education in the Austrian Empire and later practical work in Europe gave structure to these gifts. Tesla studied in Austria and Bohemia, then worked in Paris before coming to the United States. That path matters because raw imagination alone does not produce civilization-changing technology. Tesla became important because his imagination met technical training at the precise moment when industry needed new solutions. He learned enough of machinery, materials, and the failures of existing systems to recognize where conceptual breakthroughs could matter most. When Tesla moved toward the electrical centers of Europe and then to the United States, he entered a world already crowded with competition, patents, commercial interests, and public excitement. Electricity was no longer a hidden scientific curiosity. It was becoming a contest over the shape of the future. In such a world, many bright minds can vanish because they cannot connect idea to implementation. Tesla did connect them, at least in the most important phase of his career. He worked briefly for Edison after arriving in the United States, then moved into the independent work that would define his lasting reputation. Still, it is important to clear away some of the mythology that later grew around him. Tesla has often been portrayed either as an almost supernatural prophet or as a neglected magician of science whose every claim was vindicated by the future. Neither picture is accurate. Some of his ideas were sound and transformative. Some were ambitious, but only partly feasible. Some drifted beyond what experiment or physics could support. Understanding his mind requires preserving that distinction. Tesla was not important because he was right about everything. He was important because he was right about several things that mattered immensely, and because even his speculative work reflected a mind trying to extend the reach of electromagnetic thinking into a wider future. This balance between rigor and imagination is one reason Tesla remains fascinating today. He took known principles and saw fresh architectures in them. He sensed, before many others did, that electrical power would not remain local, awkward, and limited. He imagined systems that were distributed, coordinated, dynamic, and scalable. Modern life, with its vast power networks, motors, communications technologies, and invisible energetic infrastructure, still carries traces of that way of seeing. Even the unit named Tesla, used for magnetic flux density, offers a quiet symbol of this connection. It does not mean Tesla founded all of magnetism, or that his work alone defines electromagnetic science. Rather, it reflects the lasting association between his name and the practical understanding of powerful magnetic effects within electrical technology. In a small but meaningful way, modern measurement itself remembers him. So, when we ask what kind of mind Nikola Tesla had, the answer is not simply that he was ahead of his time. That phrase is too vague and too romantic. A more precise answer is that he possessed an unusual combination of visual reasoning, system-level intuition, technical skill, and relentless concentration. He could imagine invisible processes as organized patterns. He could treat electricity not as a curiosity, but as an environment of forces waiting to be shaped. He could bridge the gap between concept and mechanism more effectively than most of his contemporaries, and in doing so, he helped turn electromagnetism from a scientific triumph into a lived condition of modern civilization. There is something quietly comforting in that thought. The world can seem noisy, fractured, and unfinished, yet much of it still rests on minds that once sat in silence and tried to understand hidden order. Tesla was one of those minds. As this chapter closes, you can let that idea settle gently. Beneath the surface of the evening, beneath the rooms, the wires, and the fading thoughts of the day, there is still pattern, still structure, still a calm logic carrying energy through the dark. Chapter 2. The problem of electricity before Tesla. Before Nikola Tesla could offer a solution, electricity had to exist first as a problem. By the time he entered the field, electricity was no longer an obscure laboratory curiosity, but it was not yet the smooth, universal infrastructure we now take for granted. It was fragmented, local, technically awkward, and surrounded by unanswered practical questions. Scientists had uncovered many of the underlying principles of electromagnetism, and inventors had already built generators, motors, lamps, and transmission systems. But the world of electrical technology was still incomplete. It had pieces, not yet a fully coherent architecture. The great challenge was no longer simply to produce electrical effects. The challenge was to create a system that could generate power efficiently, move it over meaningful distances, convert it usefully into light or motion, and do so reliably enough to support modern life. The scientific foundations had been laid over the course of the 19th century. Investigators such as Michael Faraday had shown that electric currents and magnetic fields were deeply connected, and Faraday's discovery of electromagnetic induction revealed that a changing magnetic field could induce an electric current in a nearby circuit. This was a decisive insight because it meant that mechanical motion could be turned into electrical energy. It opened the path to practical generation. James Clerk Maxwell later brought the known laws of electricity and magnetism into a unified theoretical framework and showed that electromagnetic effects were not isolated tricks of wires and magnets, but expressions of a deeper field-like structure in nature. In that sense, the science had already become profound before Tesla appeared. Electricity was no longer a mysterious fluid. It had become part of a broader picture of physical reality. Yet there is a large difference between understanding a principle and building a civilization around it. Once induction made generators possible, engineers could create machines that converted mechanical work into electrical output. But early generation and distribution systems faced immediate constraints. Electrical power is not a substance that simply sits still once produced. It must be delivered under conditions that preserve usefulness. That means questions of current, voltage, resistance, heating, distance, safety, and conversion all become central at once. A laboratory demonstration can tolerate inefficiency. A city cannot. A single lamp glowing on a bench is not the same problem as a factory district, a street network, or a grid of homes. One of the most important early realities was that electric lighting itself transformed expectations. Before practical electric lighting, nighttime illumination depended on flame. Candles, gaslight, oil lamps, and related methods were dimmer, dirtier, more locally constrained, and often dangerous. When electric light became commercially plausible, people began to see electricity not only as a scientific marvel, but as a pathway to a new urban life. Illumination could become steadier, cleaner, and more widely distributed. But that promise made the distribution problem harder, not easier. Once the public expected light in many places at once, engineers needed systems capable of serving many users over a geographic area. That required solving not just how to make electricity, but how to move it well. This is where the technical limitations of early direct current systems became historically decisive. In direct current, electric charge moves in one direction through a circuit. That made conceptual sense and worked well enough for certain uses, especially over short distances. Edison's early commercial stations demonstrated that electrically powered urban service was possible, and this was an enormous step. But early direct current networks had a serious structural weakness. Transmitting substantial power over long distances without excessive loss was difficult, especially because changing voltage efficiently within those early systems was itself difficult. If a given amount of power is delivered at lower voltage, the current must be higher, and losses associated with resistance rise sharply. This meant that stations had to remain relatively close to the users they served. The system could work, but only within a fairly constrained radius. It was a local solution in a world that was beginning to demand scale. That point is essential because the pre-Tesla electrical world was not waiting for someone to discover that electricity existed. It was waiting for someone to help solve the architecture of power itself. How can generation and use be separated by meaningful distance? How can the same system serve different types of loads? How can voltage be adapted to different purposes without wasting enormous energy? How can motors be made practical, not only lamps? How can cities expand their electrical reach without building dense forests of small generating stations every few blocks? These were not minor improvements. They were the barriers between isolated electrified pockets and a genuinely electrified society. There was also a machinery problem. Early generators and motors were not ideal devices waiting to be switched on. They involved commutators, brushes, sparks, wear, and mechanical complication. Direct current machinery could function effectively, but as engineers pushed toward greater scale and power, commutation became a more serious difficulty. A machine that works modestly in one setting may become troublesome when enlarged or heavily loaded. So the pre-Tesla challenge was not only about wires stretched across distance. It was also about how to build rotating electrical machinery that was efficient, durable, and suited to widespread industrial use. Beneath the public drama of lighting and utility companies, there was a more technical problem unfolding inside the machines themselves. At the same time, alternating current was not born fully mature. Before Tesla's most important contributions, engineers in Europe and North America were already exploring alternating systems and transformers, the possibility of stepping voltage upward for transmission and downward for use gave alternating current a fundamental advantage for long-distance distribution. This was not magic, and it did not make every problem disappear, but it changed the geometry of the power problem. A system could now send electrical energy farther without suffering the same degree of loss that plagued early direct current distribution. Experimental and commercial alternating current systems began to appear in the 1880s, showing that the idea was technically powerful. But the whole system still needed conceptual refinement and practical machinery robust enough to realize its promise at scale. So, the electrical world before Tesla was not simple and not static. It was a field of partial solutions. Scientists had clarified the principles, inventors had created devices, companies had begun building commercial networks. Public excitement was growing. Yet the pieces did not yet fit together into the most effective form. Some systems favored short-range practicality. Some offered longer-range promise but lacked the fullest machinery or integration. Some engineers focused on lighting. Others thought in terms of motors, transport, industry, or communications. Electricity was becoming many things at once, and that made the need for unifying design even more urgent. There was also a cultural and economic side to the problem. New technologies do not spread only because they are scientifically sound. They spread through investment, standardization, manufacturing, public trust, and competition between rival systems. By the time electrical companies were forming in major cities, power was already becoming a commercial battlefield. Different firms backed different technical approaches, and the public did not automatically understand which system was better or why. Safety fears, promotional claims, business pressure, and patent struggles all shaped the development of infrastructure. In other words, The electrical problem before Tesla was scientific and engineering based, but it was also social. A power system had to be convincing as well as correct. This helps explain why the coming breakthrough required more than isolated brilliance. The age needed someone who could see electrical power not merely as current moving through conductors, but as an organized system of generation, transmission, transformation, and motion. That kind of thinking stands at the border of physics and engineering. It requires respect for the underlying behavior of electromagnetic fields, but also for the stubborn constraints of materials, heat, wear, and geography. The reason Tesla matters historically is that he arrived at a moment when electricity had become too important to remain piecemeal. The world needed a cleaner architecture. It needed a way to think at the scale of systems. Looking back now, it can be easy to imagine that electrification was inevitable, as though cities, factories, and homes were always destined to glow with the push of a switch. But history rarely feels inevitable from the inside. For the people living through that transition, the future of power was still unsettled. Different standards competed. Different machines failed in different ways. Distance remained a stubborn enemy. Cost constrained vision. The shape of the electrical world had not yet been decided. What existed was possibility, mixed with friction. In that unresolved landscape, the central pre-Tesla problem can be stated very simply. Humanity had learned enough about electricity to know that it could transform civilization, but had not yet fully learned how to organize that force into the most powerful and scalable form. The science had revealed the door. Industry had begun to push it open, but the wider world was still standing at the threshold, not yet fully inside. There is something strangely moving in that unfinished moment. A civilization could sense that a new kind of power was near, but could not yet hold it properly. The laws of nature were already there, quiet and exact, waiting to be arranged into human use. And perhaps that is often the way history changes. The universe does not hide its patterns forever. It lets them appear gradually until one era feels the outline of what is possible and another finally learns how to live inside it. Beneath the rooms, the wires, and the fading thoughts of the day, there is still pattern, still structure, still a calm logic carrying energy through the dark. Chapter 3. The Rotating Magnetic Field, Tesla's Greatest Insight. The breakthrough that most clearly reveals Nikola Tesla's mind was not simply a new machine, but a new way of organizing motion out of invisible forces. Before this insight, electric motors already existed, but many of them depended on mechanical switching arrangements that limited efficiency, created sparking, increased wear, and made large-scale practical use more difficult. Tesla's great contribution was to see that the magnetic field itself could be made to move in a smooth, continuous way, and that this moving field could pull a rotor into motion without the same dependence on a commutator. Britannica describes Tesla as the inventor who discovered and patented the rotating magnetic field, the basis of most alternating current machinery, and this is not an exaggeration of his significance. It identifies the core principle behind one of the most important families of machines in modern industry. To understand why this mattered so much, it helps to step away from the image of a motor as a metal box and think instead about the deeper physical problem. A motor must convert electrical energy into mechanical rotation. That sounds simple in the abstract, but the difficulty lies in creating torque continuously and efficiently. Earlier direct current motors could certainly rotate, but they relied on switching the direction of current within the rotating part of the machine so that the magnetic forces kept pushing in the same general direction. This switching was handled by the commutator and brushes, and while that approach worked, it introduced friction, sparking, maintenance problems, and practical limits. The machine could rotate, but it did so through a more awkward electrical conversation between stationary and moving parts. IEE's historical discussion notes that the commutator was undesirable because it added friction, wasted energy through sparking, and wore out. Tesla's insight was to move the problem into the field itself. If several stationary windings are arranged around a stator and supplied with alternating currents that are shifted in phase relative to one another, the magnetic effect produced by those windings does not merely grow and shrink in place. The combined field rotates. Britannica's engineering explanation describes how three equal sinusoidal currents, displaced in time and flowing in stator windings displaced in angle, produce a rotating magnetic field of essentially constant magnitude. That point is profound. Nothing mechanical needs to rotate first in order to create that rotating magnetic pattern. The coils remain fixed, but the field turns in space. In other words, motion appears first as a property of organized electromagnetism. That is why the rotating magnetic field was such an elegant idea. It replaced a choppier, contact-based method of sustaining rotation with a cleaner geometric one. Instead of forcing the rotor through repeated electrical reorientation, by physical switching, the machine could present the rotor with a magnetic environment that was already turning. A properly designed rotor would then respond to that moving field. In an induction motor, the changing magnetic environment induces currents in the rotor, and those induced currents interact with the stator field to generate torque. Britannica explains that the rotor conductors are arranged so that the rotating field induces the needed current in them, and the rotor speed settles slightly below field speed so the induction process can continue. That small mismatch is essential because if there were no relative motion at all, there would be no ongoing induction in an induction motor. Tesla's own path toward this idea began earlier than the patents that made him famous. Britannica notes that while studying at Graz, he first saw the Gram dynamo, which could operate as a generator and, when reversed, as a motor, and that he conceived a way to use alternating current to advantage. Later, in Budapest, he visualized the principle of the rotating magnetic field and developed plans for an induction motor. This sequence matters because it shows the insight did not appear as a lucky afterthought. It emerged from sustained thinking about the weaknesses of existing machines and the possibilities hidden inside alternating current. The rotating magnetic field was the conceptual bridge between alternating electrical supply and practical rotary motion. What made this more than a narrow engineering trick was that it fit naturally into the broader rise of polyphase power. A rotating magnetic field is most cleanly produced when multiple alternating currents are offset in phase and applied to windings distributed around the stator. Britannica's motor article emphasizes that a three-phase system creates a rotating field with a nearly constant magnitude, and IEE's historical discussion notes that this is one reason three-phase power became so important. The field does not merely pulse, it rotates steadily. That steadiness matters because it gives the motor smoother torque and makes the overall system more suitable for industrial use. So, Tesla's insight was not just about a single motor. It aligned beautifully with an entire architecture of power transmission and utilization. This is where the scientific beauty of the idea becomes visible. Alternating current had often been treated mainly as a rival to direct current in the contest over transmission. But Tesla saw that alternating current could do more than travel advantageously. It could create an entirely different kind of machine logic. By spacing windings in angle and supplying them with currents offset in time, one could convert temporal rhythm into spatial motion. That may sound abstract, but it's a deep physical move. The field is not pushed around by gears. It rotates because the pattern of electrical excitation has been arranged so that the vector sum advances around the machine. The result is one of those rare cases in the history of technology where an engineering advance also feels like a clarification of nature's language. It is also important to be historically careful. Tesla was not the only person associated with the emergence of the induction motor and rotating field ideas. The broader history includes parallel work by other investigators, especially Galileo Ferrari's. IEEE's historical essay explicitly notes that these ideas were in the air in the late 19th century, and that Ferrari's has a serious claim in the story. But the same discussion also explains that Tesla's work, especially with Westinghouse, helped bring a new level of efficiency and practical implementation to alternating current power and motors. In the history of technology, priority and impact are not always identical. An idea may be approached by more than one mind, yet one figure may still become central because he patents it effectively, integrates it into a wider system, and helps drive its adoption into the real world. Tesla's place in this story remains secure because his contribution was not just conceptual but systemic. The rotating magnetic field also solved a psychological problem of engineering, not just a mechanical one. It allowed designers to trust an invisible order. Electricity is difficult for human intuition because it does not behave like a solid object one can watch directly. Wires look still even when powerful currents are passing through them. Magnetic fields cannot be seen with the naked eye. Yet inside the induction motor, the essential moving part begins as a pattern that no eye can see directly at all. The machine works because electromagnetic relations are arranged correctly, not because an obvious visible agent is turning a crank. In that sense, Tesla's insight belongs to a larger transition in modern technology, where control increasingly depends on understanding structured invisibles rather than merely manipulating visible mechanisms. Once realized practically, the consequences were enormous. Induction motors became exceptionally valuable because they were rugged, efficient, and well-suited to industrial service. Britannica notes that a majority of three-phase induction motors operate directly from three-phase electric supply, which reflects how deeply this principle became embedded in real power systems. Motors based on the rotating magnetic field became workhorses of modern civilization, driving pumps, fans, compressors, conveyors, machine tools, and countless industrial processes. When people think of electrification, they often imagine lamps first, but in historical and economic terms, the ability to deliver rotary power cleanly and at scale was just as transformative. Factories do not run on illumination alone, they run on motion. Tesla understood that, and this is one reason the rotating magnetic field deserves to be called his greatest insight. The later Tesla coil is more theatrical in the popular imagination, and his wireless ambitions are more mythic, but the rotating magnetic field changed the actual machinery of the world more profoundly. It gave alternating current not only a transmission advantage, but a motor advantage. It linked power generation, transmission, and use into a more coherent whole. It reduced dependence on mechanically troublesome commutation in important classes of machines. And it did so through a principle that was physically elegant enough to remain central long after the personal drama of Tesla's life had faded. There is another reason this chapter matters in the story of Tesla. It shows that his greatness was not mainly in prediction or spectacle, but in disciplined imagination. He was able to look at alternating current and ask not merely how it could light a lamp, but what kind of spatial order it could create. That is a rarer question. It is the kind of question that sees beyond the immediate function of a technology and into its hidden generative principle. Once such a principle is found, many devices can follow. Tesla's patents and later commercial success were important, but behind them stood something quieter and more fundamental: the ability to think of force as form, and of form as something that could be made to move without direct mechanical contact. The rotating magnetic field also reveals a broader truth about physics and engineering. Nature often permits elegant solutions, but only when someone asks the right question. The materials were already present: copper, iron, coils, magnets, alternating currents, and generators all existed in some form. The missing element was not substance, but arrangement. Once the relations were understood properly, a new world of machines became possible. This is one of the humbling features of scientific history. Entire eras can stand close to a solution without yet seeing its simplest organizing idea. Then, one insight changes the scale of what can be built. So when we speak of Tesla's greatest insight, we are really speaking of a moment when invisible structure became usable destiny. A field that rotates cannot be held in the hand. It leaves no solid trace of its turning. And yet from that unseen motion came real motion in mills, workshops, transit systems, and factories across the modern world. There is something quietly existential in that. Much of reality works this way. The deepest patterns are often the least visible, and still they carry the weight of civilization. Human life, too, is often guided by forces we do not see directly at first, only later noticing the motion they have already set in us. Chapter 4: Alternating Current and the System that Powered the Modern World. Nikola Tesla's most important achievement was not simply that he supported alternating current over direct current, but that he helped turn alternating current into a complete and practical system. That distinction matters. A civilization is not changed by a preference for one kind of current alone. It is changed when generation, transmission, transformation, and use begin to fit together in a way that can scale beyond the laboratory, beyond the workshop, and beyond a few blocks of a city. Tesla's work became historically decisive because alternating current was not merely a scientific curiosity or a commercial rival. In his hands, and later in partnership with George Westinghouse, it became an architecture for modern electrification. Britannica identifies Tesla as the developer of the three-phase system of electric power transmission and the discoverer of the rotating magnetic field that became the basis of most alternating current machinery. To understand why this mattered, it helps to think of electricity not as a single invention, but as a chain of linked problems. A generator must first produce electrical energy. That energy must then travel from where it is created to where it is needed. Along the way, the system must manage losses, adapt voltage to different uses, remain safe enough for real environments, and finally deliver useful work, whether in the form of light, heat, or motion. Before alternating current matured, this chain was fragile. Power could be generated, yes, and it could be used, but connecting those steps across meaningful distance remained difficult. Direct current systems worked especially poorly when they had to serve large areas from central stations, because they could not easily change voltage in the flexible and efficient way that broader distribution demanded. The pre-Tesla electrical world was therefore full of promise, but still structurally constrained. Alternating current offered a way out of that trap because it behaves differently in time. Instead of flowing continuously in one direction, it reverses periodically. Britannica defines alternating current as a flow of electric charge that periodically reverses direction, increasing, decreasing, crossing zero, reversing, and repeats that cycle continuously. This reversible character turned out to be far more than a theoretical detail. It made possible one of the most important devices in the history of infrastructure, the transformer. With alternating current, voltage could be increased for transmission and then reduced again for practical local use. That meant electrical energy could be sent over long distances at higher voltage and lower current, reducing resistive losses in the lines, then converted downward to safer and more usable levels near homes, businesses, and factories. In that simple but powerful flexibility lay the core advantage of alternating current as a system. Tesla understood that alternating current was not just another way to light bulbs, it was a way to redesign the entire electrical landscape. His polyphase system, especially in its three-phase form, gave alternating current a deeper coherence. Three-phase power is not simply more electricity. It is a particular arrangement in which multiple alternating currents are offset in time from one another. Britannica's generator and motor explanations note that three-phase systems produce distinct currents and voltages shifted relative to one another, and that this arrangement has major practical advantages for transmission and motor operation. In such a system, power delivery becomes smoother, machines run more effectively, and motors can use the rotating magnetic field principle with exceptional success. Tesla's genius was to recognize that these were not isolated conveniences. Together they formed the basis of a superior electrical civilization. This is why alternating current won not only as a scientific idea, but as an infrastructure strategy. A central generating station no longer had to remain very near every customer. Power could be produced where fuel, water, or other mechanical resources made generation favorable, then transmitted outward to distant loads. That changed the scale of what electrical networks could become. Instead of many tiny islands of generation serving only nearby users, large systems could begin to connect wider territories. The National Park Service's history of hydroelectric development states plainly that Westinghouse, using a complete alternating current system developed by Tesla, won the long contest between alternating and direct current when power from Niagara Falls was harnessed and transmitted to Buffalo. The significance of that moment lies not only in symbolic victory, but in proof. alternating current showed that large-scale, long-distance electrification could work in practice. Niagara matters in this story because it represented more than engineering success. It was a demonstration that natural energy on a grand scale could be converted into widely distributed modern power. The falls themselves had long been a symbol of raw mechanical force in nature. The key question was whether that force could be transformed into electricity and carried beyond the immediate area efficiently enough to matter. The historical record from the National Park Service and IEEE's history of electric power shows that this became a proving ground for alternating current. Tesla's polyphase approach and Westinghouse's machinery gave the project the structure it needed. Once that model succeeded, the future direction of electrical power became far clearer. The age of local limitation was ending. Still, it would be misleading to imagine that alternating current triumphed only because one inventor had a better idea. Large technical transitions require many layers of success at once. Scientific principles must be sound, machines must be manufacturable, investors must believe the system can earn returns, public authorities and customers must trust it, engineers must be able to maintain it. Standards must become stable enough that growth does not collapse into chaos. Alternating current succeeded because it met these demands more convincingly over time. Tesla's role was crucial because his inventions and patents strengthened the system at its most important points, especially in motors and polyphase design. But his work gained world-changing force because it entered a larger industrial ecosystem ready to build on it. The motor question was especially important. Electrification was never only about illumination. A modern economy also needs motion. It needs machines that can drive pumps, factory belts, compressors, fans, transport systems, and industrial processes of every kind. Alternating current became vastly more powerful as a civilization-scale system once it could serve both transmission and rotary power effectively. Britannica notes that a majority of three-phase induction motors operate directly from three-phase electric supply, which shows just how naturally Tesla's motor ideas fit into the broader alternating current network. Generation, transmission, and use no longer had to remain awkwardly separate technical domains. The same system that moved power over distance could also drive robust motors in practical settings. That was one of the deepest reasons alternating current became the backbone of modern industry. There is an elegance in this that is easy to overlook today because we live inside the finished result. When people flip a switch or hear the hum of equipment in a building, they are usually not thinking about phases, voltage conversion, or line losses. The infrastructure works so quietly that it becomes almost invisible. But that invisibility is the mark of success. The best large systems disappear into ordinary life. Alternating current became powerful not because it was dramatic, but because it could be organized into reliability. It could travel, adapt, and serve different purposes without demanding constant attention from the people who depended on it. In a sense, Tesla helped create one of the first truly planetary kinds of technical background order. It is also worth noticing that alternating current did not make direct current meaningless forever. In certain applications, direct current remained useful, and in some modern long-distance transmission settings, high-voltage direct current has become important again for particular engineering reasons. But that later complexity does not change the historical reality of Tesla's era. At the time, the world needed a scalable, flexible, and practical system for widespread electrification. Alternating current provided the decisive answer. It solved the urgent problems of that moment more effectively and more broadly than the competing systems available to 19th-century industry. The historical victory of alternating current was therefore not an absolute philosophical verdict on all electricity for all time. It was a technological triumph in context, and it was enormous. Tesla's contribution also reveals something important about how technological revolutions really happen. They are rarely just about discovering a new force of nature. More often, they depend on identifying the right organizational principle. The laws of electromagnetism already existed. Generators already existed. Wires, coils, lamps, and motors already existed in partial form. What was missing was a unifying design logic strong enough to connect them into a self-reinforcing whole. Tesla saw that alternating current, especially in polyphase form, could provide that logic. He did not invent nature's fields, but he saw more clearly than most of his contemporaries how those fields could be arranged into a durable world system. That is why the story of alternating current should not be reduced to a simple rivalry or a personal feud. The deeper story is that one electrical architecture could remain relatively local and mechanically constrained, while the other opened the possibility of broad distribution, flexible voltage transformation, and powerful motor applications. Alternating current was not merely better at one task. It was better at becoming a complete environment for power. Once that became visible, the future of electrification changed direction. Cities could expand differently. Industry could reorganize differently. Remote energy sources could be brought into wider use. The night itself could be remade. Seen from a distance, Tesla's alternating current system was one of those rare human achievements that feels both mechanical and civilizational at once. It transformed copper, iron, magnetic fields, and rotating machinery into a shared condition of modern existence. It made possible not just devices, but patterns of life, illuminated streets, electrified industry, urban growth, powered transit, and the countless hidden motions beneath modern comfort. What looks like a technical system is also, in a quieter sense, a way of organizing human time. Work could continue after sunset. Cities could pulse through the night. Distance became less final. Energy could be moved away from its source and woven into daily life almost anywhere. And there is something existential in that transformation. A current that reverses, oscillates, and returns became the foundation of permanence in the modern world. The very thing that changes direction over and over again became the means by which civilization gained steadiness. Perhaps that is part of why this chapter still resonates. Reality often builds continuity, not from stillness, but from rhythm. The lights remain on because motion never quite stops. And perhaps human life is not so different. We endure not by holding one fixed state forever, but by finding a pattern that can keep flowing through change. Chapter 5. The War of Currents. Science, Business, and Public Fear. The conflict remembered as the War of Currents was never only a technical disagreement about wires and generators. It was a struggle over which electrical system would shape modern civilization, and because so much money, prestige, and industrial power depended on the outcome. The argument quickly expanded beyond engineering into propaganda, politics, and fear. By the late 19th century, electricity had already moved from scientific demonstration into commercial reality. Cities wanted light. Industry wanted power. Investors wanted control of the infrastructure that would define the future. In that environment, direct current and alternating current were not simply rival methods. They were rival visions of how the electric age would be built. The U.S. Department of Energy describes the conflict as a battle that began in the late 1880s between Thomas Edison's direct current approach and the alternating current system championed by Nikola Tesla and George Westinghouse. At the scientific level, the disagreement had a clear foundation. Direct current flows in one direction, while alternating current reverses direction periodically. That difference sounds modest at first, but it had enormous practical consequences in the electrical world of the time. Direct current could work well over shorter distances and had the advantage of being part of Edison's early commercial lighting system. But alternating current could be transformed much more easily to higher or lower voltages, and that made it far better suited for transmitting power over long distances with lower losses. This was not a matter of opinion or marketing language. It was a systems-level engineering reality. The Department of Energy notes directly that direct current was not easily converted between voltages, while alternating current could be converted relatively easily by means of a transformer. Britannica's History of Westinghouse likewise explains that imported transformer-based alternating current systems from Europe gave AC a decisive transmission advantage. That technical difference mattered because the scale of electrification was changing. If electricity were only needed within a few rooms or a tightly bounded district, then direct current could remain competitive. But the ambitions of the new electric age were much larger than that. Cities were growing. Commercial districts needed service across wider areas. Industry wanted centralized power that could be generated efficiently and distributed flexibly. Alternating current fit that future far better because it could step voltage upward for transmission and downward again for practical use. In other words, AC was not merely another current. It was a more scalable infrastructure logic. That is why the conflict grew so intense. The companies fighting over current were really fighting over the map of the coming world. Thomas Edison's position in this battle was complex. He was not irrational, nor was he simply a villain resisting progress. He had built a real and historically important direct current system at a time when commercial electric lighting was still new. He also had patents, investments, and a business model tied to that system. From his perspective, alternating current threatened not only a technical preference, but an entire industrial structure. The Department of Energy notes that Edison had royalties tied to his direct current patents and began a campaign to discredit alternating current when AC threatened that position. This does not mean his concerns were wholly invented. High voltages did carry danger, and poorly installed electrical systems could kill. But in the war that followed, legitimate safety concerns were amplified, dramatized, and weaponized for commercial ends. This is where the conflict became darker. Edison and his allies promoted the claim that alternating current was uniquely deadly. Public demonstrations were staged in which animals were electrocuted with alternating current in order to associate AC in the public mind with violence and hazard. The Department of Energy states plainly that Edison spread misinformation about AC's danger and publicly electrocuted stray animals to prove his point. The historical record also shows efforts by anti-AC campaigners to tie Westinghouse machinery to the development of the electric chair in New York, so that execution itself would become symbolically linked to alternating current. Britannica's Westinghouse article notes that direct current advocates attacked AC as a menace to human life and pushed a standard Westinghouse AC generator into use as the official means of execution in New York State. The technical argument had now become theater, and the theater was meant to frighten the public into associating one system with death. Yet the public fear campaign worked only because the fear had some intuitive basis. Electricity was new, largely invisible, and poorly understood by most people. A flame can be seen and judged at a glance. A moving belt or turning wheel gives visible warning. Electricity does not. A wire may appear harmless even when carrying lethal potential. In the 1880s and early 1890s, the average person had little reason to feel calm around such a force. Reports of accidental electrocutions caused by overhead lines, poor installations, or high-voltage systems were real enough to feed newspaper attention. So the War of Currents was not built on pure invention. It was built on the manipulation of a genuine anxiety, the fear of an invisible power entering daily life faster than public understanding could keep pace. For George Westinghouse, the conflict required both technical confidence and political patience. Westinghouse was not primarily a theoretician. He was an industrial strategist who understood systems, standardization, and the importance of making technology work at scale. Britannica describes him as the industrialist chiefly responsible for the adoption of alternating current for electric power transmission in the United States. He recognized early that alternating current, especially when combined with improved transformers and later Tesla's motor patents, could become a complete power system rather than a narrow specialty. That made him the ideal commercial counterpart to Tesla's more inventive and visionary style. Together, though in very different roles, they helped turn AC from a technical possibility into a competitive industrial reality. Tesla's role in the War of Currents should also be understood carefully. Popular culture often frames the conflict as a simple Edison versus Tesla duel, but the reality was more structural. Tesla's inventions mattered enormously because they strengthened the alternating current system where it most needed strength, especially through the polyphase motor system and rotating magnetic field. But Tesla was not the sole commander of the AC side. Westinghouse built the company and the infrastructure. Engineers refined transformers, generators, and measuring equipment. Investors financed expansion. Patent lawyers fought battles in parallel with technical teams. The War of Currents was therefore not a duel of isolated geniuses. It was a contested industrial ecosystem in which Tesla provided some of the most decisive technical elements. The public turning point came when alternating current began proving itself in highly visible demonstrations of scale and flexibility. One of the most famous examples was the World's Columbian Exposition in Chicago. The Department of Energy records that Westinghouse won the contract to electrify the fair using Tesla's alternating current system at a substantially lower bid than the direct current alternative. This mattered because the fair was not a private lab or remote installation. It was a public spectacle of modernity. AC did not merely survive criticism there. It illuminated one of the great symbolic stages of the age. People could see that alternating current was not only dangerous in the way Edison's campaign suggested. It was practical, versatile, and capable of powering a dazzling modern environment. The deeper industrial victory came with Niagara Falls. There, the question was no longer simply which system looked more impressive in a city or exposition. The question was whether the power of a major natural resource could be converted into electrical energy and transmitted effectively to a distant city. The Department of Energy notes that Westinghouse, having licensed Tesla's polyphase induction motor patent, won the Niagara contract, and that Buffalo was lit with alternating current from Niagara not long afterward. This success did not merely embarrass the direct current camp. It demonstrated that AC could do what modern civilization increasingly needed most: separate the site of generation from the site of use by a meaningful distance. Once that became real, the technical direction of the future was effectively decided. Still, the end of the war of currents was not an instant collapse of direct current into irrelevance. The Department of Energy notes that direct current has remained useful in some applications and has even found new importance in certain modern contexts. But the historical war of the late 19th century was decided in favor of alternating current because AC better matched the central challenge of widespread electrification in that era. It was cheaper to distribute at scale, more adaptable across voltage levels, and increasingly well supported by motors and generators suited to industrial needs. Even General Electric, after Edison's personal influence weakened, moved toward AC equipment. By the time Niagara succeeded and major public demonstrations had shifted opinion, the industrial logic was no longer in doubt. What makes the War of Currents so enduring as a story is that it reveals how scientific truth rarely travels alone. A technically better system may still need allies, capital, persuasion, standards, and public acceptance before it can prevail. Fear can delay good ideas. Reputation can distort engineering judgment. Commercial loyalty can turn into moral language and pretend to be principle. The conflict shows that modern infrastructure is not built only from copper, iron, and equations. It is also built from trust, narrative, and the willingness of a society to let invisible systems enter ordinary life. There is something quietly existential in that. The world we inhabit is often shaped not only by what is true, but by what people are ready to believe about truth. An unseen current can become light, fear, power, or death, depending on how it is understood and used. And, perhaps, human life follows a similar pattern. We move through invisible forces all the time, guided by convictions, anxieties, and unseen structures, hoping that what carries us forward is the deeper pattern rather than the loudest fear. Chapter 6: Resonance, High Frequency, and the Tesla Coil. By the time Nikola Tesla had helped establish alternating current as the foundation of modern electrical power, he had already shown that he could think in systems. But the next stage of his work revealed something different. It showed that he was not interested only in solving the practical problem of how to move energy from a generator to a motor. He also wanted to explore how electricity behaved when pushed into more unusual regimes, especially at much higher frequencies and voltages than were common in ordinary power engineering. In this phase of his work, Tesla moved closer to the boundary where practical engineering, experimental physics, and spectacle could briefly occupy the same space. The device most closely associated with this period is the Tesla coil, which Britannica describes as a resonant transformer invented by Tesla in the early 1890s to generate very high voltage, high-frequency alternating current. To understand why this chapter matters, it helps to begin with the idea of resonance itself. Resonance is one of the most general concepts in physics. It appears whenever a system can oscillate and is driven in a way that matches or approaches its natural pattern of oscillation. When that happens, energy transfer can become especially effective. One does not need advanced mathematics to sense the principle. A swing responds most strongly when pushed in rhythm with its own motion. A musical string vibrates most powerfully at certain characteristic patterns. Electrical circuits can behave in a comparable way. because coils and capacitors are able to store and exchange energy back and forth between magnetic and electric forms. When arranged properly, they do not merely carry current, they oscillate. Britannica's coverage of the Tesla coil and transformer operation emphasizes that resonance is one of the key principles behind the coil's ability to induce very high voltages. This was the conceptual opening Tesla seized upon. Ordinary power systems operated at relatively low frequencies suited to generation, transmission, and practical loads such as lamps and motors. Tesla became increasingly interested in what would happen if alternating current were driven much faster into ranges where new effects in lighting, discharge, coupling, and apparent wireless transfer could be explored. Historical accounts from Britannica and IEE-linked sources note that in the early 1890s, Tesla turned his attention toward high-frequency and high-voltage phenomena, using resonant circuits and oscillatory transformers to investigate them. That shift did not mean he had abandoned serious science for theatrical experimentation. It meant he had begun asking a different class of question, not simply how electricity could power the world, but how far the behavior of alternating electrical systems could be extended. The Tesla coil itself is best understood not as a mysterious generator of lightning, but as a resonant transformer circuit. In modern descriptions, it typically includes a power source, a device that raises voltage, a capacitor, a primary coil, a spark gap or other switching method, and a secondary coil tuned so that energy can transfer efficiently through resonance. Britannica explains that a modern Tesla coil usually begins with a transformer that boosts the input voltage and charges a capacitor connected to the primary coil. When the capacitor reaches a sufficient voltage, the spark gap conducts, causing rapid oscillation in the primary circuit. That oscillation couples energy into the secondary coil, where the voltage can rise to an extremely high level. The important point is that the great voltage increase is not due to a single simple step-up action alone. It depends on oscillatory energy exchange and tuned interaction between circuits. This is where Tesla's deeper physical intuition becomes visible again. He was not content merely to raise voltage by ordinary transformer methods. He exploited resonance so that the primary and secondary circuits interacted most effectively at a shared oscillatory behavior. In other words, he arranged the system so that energy transfer was enhanced by timing and tuning, not by brute force alone. IEE historical commentary describes the Tesla coil as an oscillating transformer created by using resonance in the discharge of capacitors through induction coils. That phrase captures the essence of Tesla's achievement. He recognized that electrical circuits could be made to behave dynamically, almost musically, with stored energy surging back and forth in patterned cycles. The coil was powerful because it treated electricity as oscillation first and supply second. The result was striking. Tesla coils can produce very high voltages, often enough to create visible discharges through the air. Britannica notes that the voltage can exceed very large values and that the apparatus produces high-frequency alternating current. These arcs and streamers later became the iconic public image of Tesla's work. They looked like artificial lightning, and in a limited sense, that description was fair. The apparatus made electrical breakdown of air visible. But the scientific importance was not the spectacle alone. The high voltage and high frequency made it possible to investigate unusual effects in gas discharge, electrical illumination, coupling between circuits, and the transmission of energy without ordinary metal connections over short distances. Tesla used such systems to light gas-filled lamps and to demonstrate the transfer of energy in ways that seemed astonishing to audiences of the time. One reason these demonstrations were so influential is that high-frequency alternating current behaves differently in practice from the lower-frequency power current familiar in utility systems. At high frequencies, coupling effects, capacitance, and inductive behavior become more prominent in many settings. Electrical energy can interact with nearby objects and circuits in ways that seem surprising if one expects everything to act like a simple battery and wire system. Tesla understood that such behavior could open doors to new forms of lighting and signaling. He was not alone in exploring high-frequency phenomena, but he had a special gift for dramatizing them and turning them into a coherent experimental program. Historical material from the Tesla Museum and Engineering Commentary notes that the currents produced by Tesla coils lie in the range of tens of thousands of hertz or more, and that Tesla built such devices as tools for systematic investigation, not merely for display. It is important, though, to separate what Tesla really achieved from the myths that later clustered around him. The Tesla coil did not prove that all power could be transmitted wirelessly across the globe with ease. It did not overturn the established laws of electromagnetism. It did not reveal a hidden energy source beyond ordinary physics. What it did do was provide a remarkably effective apparatus for generating high-voltage, high-frequency oscillations and for exploring what such oscillations could accomplish. Britannica states that the Tesla coil became widely used in radio technology, which is a more grounded and historically durable claim than many of the extravagant legends attached to it. In this sense, Tesla's coil belongs not to fantasy, but to the early technological culture that helped lead toward radio frequency engineering and wireless communication research. The connection to radio is especially revealing. Tesla was working in an era when the full practical future of electromagnetic waves had not yet been settled. Hertz had demonstrated electromagnetic wave propagation, and inventors across several countries were trying to determine how oscillatory electrical systems might be used for communication. A resonant high-frequency transformer was therefore not just a dramatic machine. It was part of a broader shift in technology toward tuned circuits, oscillation, and the control of electromagnetic energy at frequencies suited to signaling rather than only bulk power delivery. Historical commentary on Tesla's contribution to radio developments, along with Britannica's note about the coil's use in radio technology, shows that the Tesla coil must be understood within this larger transition. It helped make resonance a practical engineering language. There is another reason the Tesla coil mattered. It revealed Tesla's unusual relationship with demonstration. Many inventors showed their devices, but Tesla staged electrical phenomena in a way that made invisible principles feel almost theatrical. Lamps glowing without direct wired connection, crackling discharges, and coils sending arcs into darkness were not merely crowd-pleasing effects. They were a form of persuasion. They taught audiences that electricity was not just a utility hidden in wires. It was a field phenomenon, something dynamic and spatial. Tesla's public lectures in the early 1890s made this particularly clear. By placing his own body near high-frequency devices and allowing dramatic visual effects around him, he suggested that electrical science had entered a new realm. Some of this performance encouraged later myth-making, but it also helped popularize real ideas about alternating phenomena, resonance, and the emerging future of wireless methods. Still, the very features that made the Tesla coil fascinating also pointed toward the limits of Tesla's later ambitions. High-frequency resonance systems can transfer energy impressively over modest distances under carefully arranged conditions, especially through inductive or capacitive coupling. But scaling such effects into a globally efficient wireless power infrastructure is a vastly harder problem. IEEE Spectrum's critical review of wireless power notes that Tesla demonstrated wireless transmission over modest distances in Colorado Springs, but failed in the larger effort to scale the concept. That distinction is essential to preserve. Tesla's experiments were not fraudulent. They were real and often ingenious. But some later extrapolations from them moved well beyond what practical engineering could support. Even so, this chapter should not be read as a story of overreach alone. The Tesla coil remains one of the clearest expressions of Tesla's intellectual style. It combined physical intuition, engineering creativity, and a willingness to enter a regime of phenomena where the familiar behavior of ordinary circuits gave way to something more fluid and oscillatory. Through resonance, Tesla found a way to store and release energy in patterned electrical motion, and in doing so, he expanded what people thought electrical apparatus could be. He helped shift attention from electricity as mere current delivery toward electricity as controlled oscillation. That conceptual move was one of the great bridges from the power age into the communication age. In the end, the Tesla coil mattered because it made a hidden rhythm visible. It showed that electrical systems could sing, not only drive. Their energy could pulse, build, exchange, and erupt according to resonance, as though the circuitry itself had found a natural cadence. There's something quietly existential in that idea. Much of the universe works not by static force, but by patterned return, by energy moving back and forth until the right alignment gives it power. Human life can feel scattered and discontinuous, yet sometimes meaning also arrives that way, through resonance rather than command. A thought, a place, or a moment meets something waiting inside us, and suddenly what seemed silent begins to glow. Chapter 7: Wireless Energy and Wireless Communication. After helping establish alternating current as the foundation of large-scale power transmission, Nikola Tesla turned toward a more ambitious question. If electrical energy could already move through wires across cities and landscapes, could it someday move without them? And if signals could be sent through conductive networks, could information itself be launched into space and received far away without a physical connection? These were not foolish questions in themselves. By the end of the 19th century, the science of electromagnetism had already shown that electrical and magnetic disturbances could propagate as waves. Heinrich Hertz had demonstrated electromagnetic wave phenomena experimentally, and engineers across Europe and the United States were beginning to imagine new communication systems based on tuned circuits, oscillation, and radiation. Tesla entered this moment with unusual confidence, convinced that he could do more than send messages. He believed he could build a world-spanning wireless system for communication and, eventually, for power. It is important to separate these two ambitions from the very beginning because they are related but not identical. Wireless communication and wireless power are often spoken of together in Tesla's story, yet the engineering difficulty of each is very different. Sending a signal does not require delivering large, useful amounts of energy to do mechanical work. A communication system only needs to transmit structured information strongly enough for a receiver to detect and interpret it. Power transmission is far more demanding because the receiver must obtain not just information, but substantial energy. Tesla pursued both aims, and part of the fascination of this stage of his life comes from the fact that he moved between them almost as if they were different scales of the same basic dream. In one sense, he was correct. Both depend on controlling electromagnetic behavior across distance. But the practical challenges are not comparable, and history would eventually prove much kinder to his communication ideas than to his global power vision. Tesla's earlier work on high-frequency currents and resonant circuits prepared him naturally for this transition. The Tesla coil was not simply a dramatic source of sparks. It was an apparatus for generating oscillatory electrical behavior at high frequency and high voltage. And such oscillation lay near the heart of the emerging wireless age. In the closing years of the 19th century, the ability to produce, tune, and detect rapidly varying electrical phenomena became central to the development of radio. Britannica notes that Tesla's coil became widely used in radio technology, and Tesla himself received patents and recognition for wireless and radio-related work before the field settled into the more familiar narrative dominated by Marconi. This does not mean Tesla single-handedly invented all radio communication, because that history is shared and contested. It does mean that he was working within the real scientific stream that fed the birth of wireless signaling. For Tesla, wireless communication was never only about sending telegraphic clicks through the air. He imagined a broader system capable of transmitting messages, perhaps even speech and images, across great distances through carefully tuned transmitters and receivers. What mattered to him was not only that radiation could spread through space, but that circuits could be designed to resonate selectively, making transmission intelligible rather than chaotic. This interest in tuning was one of the most scientifically grounded parts of his wireless thinking. Communication requires discrimination. A receiver must respond to one intended signal and not to every disturbance in the environment. The larger wireless revolution depended on exactly this sort of control, and Tesla understood that oscillation without tuning would never become a workable global system. At the same time, Tesla's imagination went beyond what later radio would become in its simplest form. He began to envision the Earth itself as part of a giant electrical system, rather than treating wireless transmission only as radiation sent outward through open space. He sometimes described methods involving the globe, the atmosphere, and resonant electrical behavior on a vast scale. Here, the story becomes more difficult because Tesla's writings and plans combined genuine insight with speculative extrapolation. He was not ignorant of electromagnetic science. He was trying to enlarge it into a world system. But some of his claims about how efficiently energy might be transmitted globally were never demonstrated in a practical way. The surviving historical record from Wardenclyffe makes this clear. Tesla believed he could erect a powerful transmitter and send energy over long distances, possibly around the whole Earth, and he obtained funding to pursue that goal. But he never produced practical results that established the method as workable infrastructure. Before Wardenclyffe, there was Colorado Springs, and that site matters because it was the place where Tesla tested the limits of his wireless ideas on a larger experimental scale. IEE Spectrum's historical review notes that Tesla demonstrated his ability to send power wirelessly over modest distances there. That wording is crucial. It confirms that Tesla's work was not pure fantasy. He did achieve genuine wireless transfer effects under experimental conditions, but the same source also states that he failed in the larger attempt to scale the effort. This distinction should remain at the center of any scientifically honest account. Tesla proved enough to justify further curiosity. He did not prove that a global wireless power network was ready to replace wires. Why was scaling so hard? The answer lies in the stubborn physics of energy transfer. Signals can be weak and still useful if a receiver is sensitive enough. Power must remain substantial at the point of delivery. As transmission distance increases, energy tends to spread, dissipate, couple inefficiently, or encounter losses that quickly become serious. Modern wireless power methods do exist, especially over short ranges through inductive or resonant coupling, and IEEE Spectrum's discussion explicitly compares some modern demonstrations to the same underlying physics found in transformers and resonant coils. But these methods work best under controlled conditions and moderate distances. The gulf between lighting a lamp over a short separation and feeding a continent through the air is immense. Tesla was not wrong to explore the possibility. He was wrong, or at least unproven, in believing the concept could be scaled in the form he imagined. Wardenclyffe Tower became the most dramatic symbol of this ambition. Built on Long Island with support from J.P. Morgan, the project was intended to serve as a powerful transmitting station connected to Tesla's dream of worldwide wireless communication and perhaps power distribution as well. Smithsonian describes Wardenclyffe as Tesla's last great chance to secure both recognition and wealth through a worldwide wireless transmission system. The IEEE Wardenclyffe history notes that the laboratory operated in the first years of the 20th century, that the tower was massive for its time, and that Tesla hoped it would allow him to generate more power and further his wireless ideas. Yet the same historical record states that he was never able to show practical results and that funding stopped. Wardenclyffe did not fail because the dream lacked grandeur. It failed because grandeur is not the same as proof. Tesla's wireless communication ideas deserve a more favorable judgment than his wireless power ambitions. Britannica states that he pioneered the field of radio communication, and the IEEE Wardenclyffe history says he was awarded an early patent for demonstrating wireless transmission of radio waves before Marconi. The broader history of radio remains complicated because many inventors contributed and patent recognition shifted over time. But Tesla clearly belongs among the serious early contributors to wireless signaling technology. His work on oscillators, resonant circuits, high-frequency transformers, and tuned electrical behavior was deeply relevant to the emerging communications age. Even where later commercial radio took forms different from Tesla's most expansive hopes, his research formed part of the intellectual and technical ground on which that age was built. There is also a revealing psychological contrast in this chapter of his life. In alternating current power systems, Tesla's insights found strong partners in industrial practicality. The system could be built, standardized, manufactured, and demonstrated in ways that investors and engineers could trust. Wireless work brought him into a more uncertain domain, where the distance between bold concept and proven infrastructure widened sharply. Tesla remained brilliant, but he was moving into territory where vision could outrun verification. That does not make the vision worthless. In science and engineering, someone often has to imagine further than current tools can immediately reach. But the history of Wardenclyffe shows what happens when a future-seeing mind loses contact with the pace at which the world can actually build. And yet, it would be unfair to dismiss this phase of Tesla's career as failure alone. He was asking one of the most defining questions of the modern age. Must connection always depend on visible linkage? The 20th century answered that question with an overwhelming no. Radio, broadcast communication, radar, satellite links, Wi-Fi, cellular networks, and countless other technologies all emerged from the expanding control of electromagnetic transmission through space. Tesla did not create that entire world by himself, but he saw its outline early. He understood that communication could become detached from wire networks and that electrical technology would increasingly shape invisible environments around human life. In that sense, even where he overshot the physics of practical global power transfer, he correctly anticipated a civilization in which information would move through the air as a normal condition of existence. This makes Chapter 7 one of the most revealing parts of Tesla's story. It shows him at once as a rigorous experimenter, an important early wireless thinker, and a visionary whose imagination sometimes exceeded what engineering could then support. He was neither a fraud nor a prophet in the simplistic sense. He was something more interesting. A mind standing at the edge of a real scientific frontier, succeeding in some directions, overreaching in others, but helping define the questions that later generations would answer in their own ways. Wireless communication became one of the foundations of modern civilization. Wireless power became practical only in narrower forms than Tesla hoped. The distinction between those outcomes is the distinction between what he truly foresaw and what he only half caught in the distance. There is something quietly existential in that outcome. Human beings often reach toward futures they cannot fully build, and yet those attempts are not wasted. Sometimes the grand dream fails, but in failing it still teaches the world where the real path lies. Tesla wanted a planet joined by invisible energy and invisible thought. He did not achieve that dream in the form he imagined, but in another form, quieter and stranger, it arrived anyway. And perhaps that is how history often works. We don't always receive the exact future we picture. We send our hopes outward, and the world answers with something related, altered, and still enough to reshape what it means to be connected at all. Chapter 8: Colorado Springs. When Tesla tested the limits of electricity. In the summer of the late 19th century, Nikola Tesla left New York and traveled west to Colorado Springs, carrying with him not only equipment and assistance, but a far more dangerous kind of cargo: scale. Up to that point, much of his fame had come from ideas already impressive in themselves, including alternating current systems, induction motors, high-frequency experiments, and spectacular demonstrations with resonant coils. But Colorado Springs marked a change in ambition. Tesla no longer wanted merely to prove that unusual electrical effects were possible in controlled indoor settings. He wanted to enlarge his experiments until they approached the size of the Earth, the atmosphere, and the storm itself. Historical accounts from Tesla's Colorado Springs notes and later summaries make clear that he chose the site for its altitude, its dry air, its open space, and its frequent lightning, all of which he believed would favor large high-voltage experiments and the study of wireless transmission. The move was scientifically significant because Tesla was no longer investigating only devices. He was investigating propagation. A motor or transformer can be studied as a bounded machine. Wireless transmission forces a different question. How do electrical effects move through real environments, through ground, air, and space, and how far can carefully organized oscillations remain useful? Tesla's Colorado period, which ran from late spring into the first days of the following year, became the closest thing in his career to a field campaign in experimental electromagnetism. The surviving Colorado Springs notes show that he was not simply staging theatrical effects for newspapers. He kept an extensive research diary, recording measurements, ideas, apparatus changes, and observations about transmitters, receivers, the atmosphere, and the Earth itself. The station he built there was designed for scale and isolation. Tesla needed room for large apparatus and for experiments too violent for an ordinary city laboratory. Contemporary and later descriptions refer to the site as an experimental station devoted to high voltage, high-frequency electricity, and wireless telegraphy. At its center stood a giant resonance system, often described as a magnifying transmitter. This was not simply a larger Tesla coil in the casual popular sense, though it drew on related resonant principles. Tesla intended it as a powerful transmitting apparatus capable of producing enormous voltages and electrical oscillations, which he hoped could couple energy into the ground and atmosphere in ways that might be useful for global transmission. He wanted an instrument that amplified electrical action to planetary ambition. Colorado Springs offered more than empty land. It also offered natural electricity. Tesla had long been interested in lightning, and the region's storms gave him an opportunity to observe atmospheric electrical phenomena directly. Historical material from the Colorado Springs area and later museum commentary notes that Tesla built instruments to observe and measure lightning discharges and their electrical behavior. This matters because natural lightning was, in a sense, the largest electrical laboratory available to him. If the atmosphere could already sustain immense discharges, perhaps it could also participate in organized transmission. He watched storms, detected their signals, and tried to understand what the earth and sky were already doing on their own. The spectacular photographs associated with Colorado Springs have greatly shaped Tesla's legend. In them, he appears seated calmly in his laboratory while huge artificial discharges leap around him. These images are memorable because they seem to collapse science into myth, making Tesla look less like an engineer than a magician inside a storm. But the scientific reality behind them is more interesting than the image alone. Tesla was using extremely high-voltage resonant apparatus to create large electrical discharges in air, demonstrating both the scale of his equipment and the ability of tuned oscillatory systems to store and release enormous electrical energy. The goal was not simply to produce arcs for visual effect. It was to push resonant transmission systems into a regime where their behavior might reveal new possibilities for wireless transfer and for the interaction of electrical oscillations with the environment. One of the most important things to say about Colorado Springs is that Tesla did achieve genuine experimental results there. Reliable modern commentary, including engineering reviews, notes that he demonstrated wireless power transfer over modest distances. That point should be preserved carefully because it places his work between dismissal and exaggeration. He was not delusional, and he was not already powering continents through the atmosphere. He was showing that under the right resonant conditions, energy could be transferred without ordinary conductive connections over experimentally useful distances. In modern terms, that makes Colorado Springs part of the deeper history of wireless energy transfer, even if Tesla's specific global ambitions remained unfulfilled. At the same time, Colorado Springs is where Tesla's imagination began to outrun what his evidence could securely support. He became increasingly convinced that the Earth itself could be treated as a conductor within a worldwide transmission system. He wrote and later spoke as though stationary electrical waves could be established on a global scale, allowing signals and perhaps useful power to be sent to distant points with limited loss. There is a real scientific core here, because the Earth and atmosphere do participate in electromagnetic behavior, and later science would indeed study global resonances and waveguide effects in the Earth ionosphere system. But it does not follow from that fact that Tesla had solved the practical engineering problem of global wireless power. His Colorado work sharpened his belief in that possibility, yet the historical record does not show a completed system or decisive proof of global feasibility. This is the crucial line that must be held if Colorado Springs is to be understood scientifically rather than mythically. The laboratory itself became a place where the border between experiment and overreach grew thin. Tesla drove his apparatus to astonishing intensities. Reports from later historical accounts describe thunderous discharges, visible streamers, and local electrical side effects dramatic enough to enter regional lore. Some stories grew in the retelling, and not every famous anecdote from Colorado Springs is equally well supported. For example, the tale that Tesla completely knocked out the town's power system is repeated widely, but some local historical commentary warns that the evidence for that version is weak. The legends survive because the genuine experiments were already extraordinary enough to invite embellishment. What did Tesla actually learn there? He learned more about building and operating very large resonant transformers and transmitters, about the sensitivity required on the receiving side, and about treating the Earth and atmosphere as active parts of transmission rather than passive surroundings. Even where his conclusions extended too far, the experimental direction was real. He was trying to turn the whole environment into part of the circuit. Colorado Springs also matters because it changed Tesla psychologically. The site seems to have reinforced his sense that he was no longer merely improving machinery, but uncovering a new planetary order of electricity. In Colorado, he began acting more like an electrical natural philosopher of the globe. The shift is subtle but important. Once a thinker begins to see the Earth as an electrical body waiting to be tuned, the scale of his plans changes. The later Wardenclyffe project did not emerge from nowhere. It grew out of the confidence Tesla carried back from Colorado Springs, where large-scale experiments seemed to him to confirm that far more ambitious systems were within reach. Yet Colorado also revealed a recurring pattern in Tesla's career. He was often strongest when invisible principles could be converted into bounded, reproducible systems with clear practical advantages, as in polyphase alternating current and induction motors. He became less reliable when moving from elegant physical possibility to planetary engineering certainty. Colorado Springs sits exactly at that threshold. It contains genuine science, genuine instrumentation, real experimental discipline, and real technical daring. But it also contains the moment when success at one scale encouraged belief, at a much larger scale not yet justified by evidence. That is not unusual in the history of science. Many bold researchers mistake an opening for a completion. Tesla's case simply made the transition more dramatic because the forces involved were so visible and so immense. For all of that, Colorado Springs remains one of the most fascinating episodes in the history of electricity. It was a place where a single inventor tried to test not just a device, but a worldview. He asked whether power and communication might one day escape wires almost completely. He asked whether resonance could be scaled beyond rooms and buildings into the earth itself. He watched lightning and answered it with machinery. He took the laboratory outdoors into altitude, dryness, storm, and distance, as though ordinary walls were no longer sufficient for the size of the question he wanted to ask. Even where he failed at a scale that still reveals the shape of the future he was chasing. And perhaps that is why Colorado Springs still feels so haunting. It shows a human mind reaching to the edge of what it can test, where knowledge is still mixed with longing. The arcs in Tesla's laboratory were real, but so was the uncertainty beyond them. In that sense, Colorado Springs was not only about electricity. It was about the moment when thought becomes large enough to touch mystery without yet dissolving it. Perhaps that is always part of science. We build our instruments. We widen the field of the known. And still at the edge there is weather, darkness, and a silence that has not answered. Chapter 9. Remote Control, Automation, and the Future Tesla Saw. In the public imagination, Nikola Tesla is often remembered for lightning, coils, towers, and vast electrical dreams, yet one of his most revealing inventions was much smaller and quieter, a boat moving across water under command sent through space. At first glance, it may seem less grand than alternating current or wireless power, but in intellectual terms, it was one of his boldest achievements. With this invention, Tesla was no longer focused only on transmitting energy or signals. He was trying to transmit action. He wanted to show that a machine could receive instructions at a distance, interpret them through an internal arrangement of control elements, and carry out behavior without a human hand touching it directly. In that sense, the radio-controlled boat he demonstrated in New York was not merely a novelty. It was an early step toward remote control, automation, and the larger idea that intelligence-like behavior could be distributed into machines. Tesla unveiled this device at the Electrical Exhibition at Madison Square Garden in the late 19th century. Contemporary and later sources agree on the significance of the demonstration. Britannica states that in the year of the exhibition, Tesla announced his invention of a teleautomatic boat, guided by remote control, and proved his claims before a crowd when skepticism arose. The Nikola Tesla Museum similarly describes it as a pioneering step in remote control and the first public demonstration of wireless transfer of commands at a distance by radio waves. The importance of the event lies not only in priority, though priority matters. It lies in the conceptual shift Tesla was asking his audience to make. He was inviting them to see that a machine could be separated from the operator not just physically, but operationally. Command no longer had to travel through rods, ropes, wires, or direct human contact. It could move invisibly through space. This was astonishing in its time because the world had not yet fully absorbed radio itself, much less the idea of radio-based control. Today, remote control feels ordinary. A garage door opens, a drone turns, a rover moves, a satellite adjusts its orientation, and almost no one pauses to ask how strange this really is. But in Tesla's era, the dominant intuition about machines was still local. A machine was either self-contained in a narrow mechanical sense or directly linked to its operator by visible means. If it moved, someone nearby moved it, or at least a wire told it what to do. Tesla's boat disrupted that intuition. It was a machine carrying its own source of motion while accepting instructions from afar. That made it seem almost alive to many observers. Some even suspected trickery, hidden wires, or trained animals concealed inside. The disbelief itself is historically important because it reveals how radical the idea appeared. Scientifically, the device was not magic at all. It was an early control system built from radio signaling, switching, and onboard mechanisms. PBS's technical description of the boat explains that radio signals controlled switches that in turn operated the propeller, rudder, and lights. The receiving apparatus included a coherer-like radio-activated switch, along with mechanical elements that advanced contact arrangements and prepared the system for the next command. That description matters because it shows that Tesla was doing more than simply sending one impulse to trigger one action. He was building a logic of response. A signal arrived, the receiver registered it, an internal mechanism changed state, and the craft carried out a corresponding movement. In modern language, this begins to resemble a control architecture rather than a one-time wireless trick. The boat was primitive by later standards, but the principle behind it was profound. Distance could be crossed not only by energy and information, but by command. Tesla gave this broader concept a name. He called it teleautomatics. The word itself is revealing. It combines the idea of action at a distance with the idea of automatic operation. Tesla did not mean that machines had become conscious. He meant that they could be organized so as to execute intended behavior when guided through remote signals and internal mechanisms. This is one of the most forward-looking parts of his work because it shifts attention from the machine as a passive tool to the machine as a controlled agent. In later technological history, that shift becomes central. Guided weapons, industrial automation, robotic systems, remote exploration vehicles, and networked machines all depend on some version of the same basic insight. Action can be delegated to a device that is not physically attached to the person directing it. Tesla saw this not as a narrow military or recreational curiosity, but as the beginning of a wider transformation. It is tempting to say that Tesla invented robotics in the full modern sense, but that would be too loose. Modern robotics include sensors, feedback loops, autonomy, computation, machine perception, and many other layers that did not exist in Tesla's boat. Still, it is scientifically fair to say that he identified one of the foundational ideas from which later robotics and automation would grow. A machine need not be fully autonomous to participate in the history of robotics. It is enough that it receives encoded instructions, changes internal states, and produces controlled behavior without direct mechanical manipulation. The teleautomatic boat did exactly that. It was not a thinking robot, but it was a remote-controlled electromechanical system, and that fact places it in the ancestry of a very large technological family. Tesla's own interpretation of the invention went even further. He argued that increasingly sophisticated automata might one day perform complex tasks and perhaps even simulate aspects of living behavior. In his public statements around teleautomatics, he suggested that mechanisms could be made to act as though they possessed reason, even when their behavior actually arose from predetermined responses. That idea is striking because it anticipates a key tension in later technology: the difference between true thought and the appearance of purposeful action. Long before digital computers, Tesla was already exploring a world in which machines might appear to decide, not because they possessed minds in the human sense, but because their control systems were sufficiently arranged to mimic intention. He was not alone in imagining mechanical life, But he was unusually early in linking that imagination to wireless control and practical engineering. There was also a military dimension to Tesla's vision, though it did not develop in his lifetime as he expected. He believed that remote-controlled vessels or torpedoes might attract strong military interest. Historical accounts note that he tried to interest the military in such possibilities, but substantial adoption did not follow immediately. In one sense, he had seen the future too early. The communications, guidance, power, and industrial systems needed to make remotely controlled weapons broadly practical had not yet matured. It would take much later developments in radio, electronics, computation, and miniaturization before remote-guided systems became central to warfare and industry. Tesla's forecast was therefore not wrong in principle. It was premature in implementation. This pattern appears elsewhere in his career as well. A real outline of the future, glimpsed before the surrounding technological ecosystem was ready to support it. What makes the boat demonstration especially important is that it sits at the crossing point of several different technological streams. It belongs to the history of radio because it relied on wireless signaling. It belongs to the history of automation because it showed that an apparatus could translate received signals into structured action. It belongs to the history of control engineering because it involved state changes, switching, and command-response behavior. And it belongs to the cultural history of modernity because it challenged the public to imagine a world in which agency might be displaced from the human hand into hidden systems. That last point is perhaps the deepest. Once a society accepts that machines can be made to act at a distance, the meaning of presence begins to change. The operator need not stand beside the machine. Command and action can be separated across space, in time. That separation would shape everything from factories to war, from exploration to household life. Tesla also deserves credit for intuiting that future machines would not remain isolated devices. Although his own boat was a single craft receiving commands, the underlying principle points toward larger networks of controlled systems. Once commands can move invisibly and reliably, multiple machines can be coordinated. Feedback can be layered into control, and distance ceases to be a strict boundary on operation. Modern engineering would eventually generalize this into communications networks, control systems, automation infrastructure, and machine-to-machine coordination. Tesla did not build that whole future, but he clearly sensed its direction. His gift was often not to finish an age by himself, but to expose the principle around which that age would later organize. Teleautomatics was one of those principles. There is also an irony here. Tesla is often celebrated for scale, for his giant towers and immense voltages, but the remote control boat reveals his imagination just as well in miniature. It was small enough to fit into a demonstration pool, yet conceptually, it opened onto the largest questions of technological modernity. What is control? What counts as agency in a machine? How far can action be separated from the body that initiates it? How should humans relate to systems that obey them from afar, but increasingly operate beyond immediate physical touch? These are not quaint historical questions. They are the background questions of the present century. Drones, robotic vehicles, remote surgery, industrial automation, and spacecraft all live inside them. Tesla's boat did not contain the full answer, but it pointed unmistakably toward the terrain on which those answers would be sought. In that sense, Chapter 9 is not just about one invention. It is about a shift in the grammar of technology. Before, the operator and the operated device were expected to remain closely bound. After teleautomatics, a new possibility stood open. Intention could travel. Once that became imaginable, the future of machines changed permanently. Tesla's audience may have seen a curious little vessel. History can see something larger. It can see one of the first moments when human will stepped away from direct contact and began learning how to inhabit systems at a distance. There is something quietly existential in that transformation. The more powerful our technologies become, the less often they require our immediate presence, and yet they still carry our purposes into the world. A signal leaves the hand, crosses empty space, and becomes motion somewhere else. Perhaps that is why Tesla's boat still feels uncanny. It reminds us that human action is not always where the human body is, and that the future often begins the moment intention learns to travel farther than touch. Word count: approximately 1,600. Chapter 10. Tesla's Real Legacy: What He Changed in Physics and Technology. Nikola Tesla's legacy is often described in extremes. In one version, he is treated as the single forgotten genius behind nearly every modern electrical technology. In another, he is reduced to a brilliant but eccentric inventor whose fame has been exaggerated far beyond his actual achievements. Neither picture is accurate. Tesla's real legacy is more interesting than either myth. He did not invent all of modern technology, and he did not stand alone outside the work of other scientists and engineers. But he did make several foundational contributions that changed the practical development of electricity in lasting ways. And he did so at a moment when those contributions could alter the structure of modern life itself. Britannica identifies him as the inventor who discovered and patented the rotating magnetic field, developed the three-phase system of electric power transmission, and helped lay the basis of most alternating current machinery. The clearest part of Tesla's legacy lies in the world of electric power. Before electrification became a background condition of civilization, it had to be organized into a system that could actually scale. Power had to be generated, transmitted over significant distance, adapted to different uses, and converted into useful work reliably enough to support cities and industry. Tesla's role in this transformation was not that of a lone builder of every component, but that of a thinker whose most important inventions fit directly into the architecture that solved these problems. His work on polyphase alternating current and rotating magnetic fields helped make alternating current power not merely possible, but compelling as a whole system. That is why his influence survives not just in museums or biographies, but in the ordinary operation of grids, motors, and industrial equipment across the world. His greatest technical contribution was the rotating magnetic field. This was not simply one clever invention among many. It was a principle that allowed alternating current to drive motors in a far more elegant and practical way than many earlier systems. By arranging alternating current so that their magnetic effects rotated in space, Tesla helped eliminate the need for some of the mechanically troublesome switching methods that limited earlier motor designs. The result was a foundation for induction motors and related alternating current machinery that became central to modern industry. If electric light changed how people saw the night, reliable motors changed how factories, transport systems, pumps, ventilation, and countless machines actually moved. This is one reason Tesla's impact belongs not only to electrical history, but to the history of industrial civilization itself. That point is easy to underestimate because motors are less dramatic in popular imagination than sparks or towers. But the real engine of electrification was never entertainment. It was useful motion. Modern society depends on enormous numbers of machines that rotate, compress, cool, lift, pump, cut, and circulate. The commercialization of the alternating current induction motor, which followed Tesla's key insights and patents, accelerated the spread of electric power into industry. The historical record from engineering archives notes that industrial use of electricity developed rapidly after Tesla, aided by the commercialization of the AC induction motor at Westinghouse. In that sense, Tesla's legacy is embedded not only in scientific memory, but in the physical machinery of work itself. Tesla also changed technology by helping make alternating current a complete environment rather than a local novelty. A technical idea becomes historically decisive when it organizes many other devices around itself. Alternating current could be transformed between voltage levels far more flexibly than the early direct current systems of the time, and that allowed power to be sent more efficiently over greater distances. Tesla's polyphase contributions mattered because they fit naturally into this larger advantage. He helped make generation, transmission, and motor use belong to one coherent electrical world. This is why his name remains central to the story of electrification, even though many other engineers and industrialists contributed to the final infrastructure. His work did not merely improve a machine, it strengthened the logic of the whole system. Tesla's legacy also reaches into high-frequency electrical engineering. The Tesla coil, though often reduced to a symbol of theatrical lightning, was a real and important device for generating very high voltage, high-frequency alternating current. Britannica describes it as a resonant transformer capable of producing extremely high voltages. Its scientific importance lies not in spectacle alone, but in the way it helped make resonance and oscillatory behavior practical engineering tools. Tesla's experiments with such systems contributed to the early culture of radio frequency research and to broader thinking about tuned circuits, oscillation, and electromagnetic behavior at high frequency. He did not invent all of radio, and he did not single-handedly create modern communications electronics, but his work helped establish part of the technical ground from which those fields grew. This is where Tesla's legacy becomes more subtle. In electric power, his major contributions are direct and unmistakable. In wireless and radio-related fields, his role is significant but more distributed among other inventors and experimenters. He was a serious pioneer in wireless communication and high-frequency techniques, but the development of radio was a cumulative process involving several figures, overlapping patents, and rapid technical change. A truthful account must resist both simplifications at once. It is wrong to erase Tesla from the history of wireless technology, and it is equally wrong to treat all later wireless communication as his personal invention. His real importance lies in helping move engineering culture toward oscillation, tuning, resonance, and non-local transmission as serious technical possibilities. Another part of Tesla's legacy lies in remote control and automation. His radio-controlled boat demonstration showed that machines could receive instructions at a distance and respond through internal electrical arrangements without direct human contact. That invention did not create modern robotics in the full contemporary sense, but it did reveal one of the key principles behind later automation. Control can be separated from physical proximity. Commands can travel through space and still become around motion somewhere else. In a century shaped increasingly by remote operation, autonomous systems, and distributed control, that idea proved historically deep. Tesla's boat was not a final technology. It was an early sign that machines would eventually become extensions of human intention far beyond the reach of direct touch. Perhaps the most difficult part of Tesla's legacy is the boundary between what he truly changed and what he merely anticipated. He genuinely transformed alternating current technology. He genuinely helped shape the development of high-frequency electrical experimentation. He genuinely pioneered remote control. But some of his grander visions, especially worldwide wireless power on the scale he imagined, were never realized in the form he proposed. This does not make those ambitions fraudulent, but it does place them in a different category. They belong less to demonstrated engineering legacy and more to speculative foresight. A fair judgment of Tesla must preserve that distinction. He was at his strongest when invisible physical principles could be turned into bounded systems with reproducible practical value. He was less reliable when large conceptual possibilities outran the evidence of scalable implementation. That distinction matters because Tesla's legend has often been inflated by disappointment as much as by admiration. People are drawn to figures who seem to have been misunderstood by their own age. Tesla's later life, marked by financial struggle and increasingly extravagant claims, made him especially vulnerable to posthumous myth-making. In popular culture, he has sometimes become a vessel for fantasies about suppressed inventions, hidden energy sources, or futures denied by conspiracy rather than by engineering difficulty. Yet the truth needs no such decoration. His actual achievements were already extraordinary. He helped give modern civilization one of its essential electrical foundations. He contributed important tools and ideas to the emerging world of high-frequency and wireless engineering. He foresaw key aspects of remote-controlled technology. He did enough in reality that fiction has never been necessary. What Tesla changed in physics then must be stated carefully. He did not revolutionize theoretical physics in the manner of Maxwell or Einstein. He did not introduce a new fundamental law of nature. His impact on physics was more practical and technological. He expanded what physicists and engineers could do with electromagnetic principles already known in broad outline. He turned parts of field theory into machinery, oscillation into apparatus, and electrical insight into infrastructure. In many periods of history, the person who changes civilization most is not the one who writes the deepest equation, but the one who discovers how a principle can be made to work at scale in the world people actually inhabit. Tesla was one of those people. And what he changed in technology is even clearer. He helped make electricity mobile across distance, useful in motion, expressive in oscillation, and obedient at a distance. He belonged to the generation that transformed electricity from scientific wonder into an operating condition of modern life. Once that happened, everything else could begin to build on top of it. Industry, communications, automation, urban growth, and the everyday assumption that energy and control could be summoned almost instantly. Tesla did not build the entire modern world by himself, but he helped make part of its foundation stable enough for the rest to rise. There is something quietly existential in that kind of legacy. Most human beings leave behind objects, memories, perhaps a few altered lives. Tesla helped leave behind conditions. He changed the background rules of what later generations could assume was possible. Much of the modern world now hums with forces he helped organize, even when his name is not spoken. And perhaps that is one of the strangest forms of permanence. A person disappears, but a pattern remains active in the world, carrying energy long after the mind that first imagined it has gone still. And now, my friend, as Tesla's story fades into the night, you can let these ideas soften and drift with you into sleep. If you're still awake, there's another video waiting for you on this channel. But if not, close your eyes, rest gently, and sweet dreams among the stars.